from adaptation. Okay? Perfect alternation. It's a very fast switch, okay, because the adaptation is very slow. There's a fast time scale and a slow time scale. Physicists would look at this and say it's a relaxation oscillation between these two populations. Rapid switch. Okay, so first question. Does this model satisfy Levelt's proposition 4? That is, if we increase the intensity of the sensory input, do we increase the speed of the switches? Okay. So here is a plot of the period as a function of input strength, the same to the two populations. So this is for different strengths of inhibition. So look at this curve right here. Okay. This is not a monotonic curve. Okay, it's very symmetric. Okay, this would be Levelt's branch right here. This corresponds to more rapid switching than with increasing strength. But there's another branch to this curve too, in which the period of population switching rate is slowing down as you increase. It's a very symmetric picture. Okay, very symmetric. The input-output function was very symmetric Boltzmann function. Okay, that's key in getting these perfect symmetric curves. If the inhibition is very strong, okay, then there's no switching within this region here. If the inhibition is very strong, boom, then somebody stays down. Some population stays up, the other population stays down. You do not get switching. The adaptation cannot overcome. Okay? So this model has a range of different dynamical regimes depending upon parameters. Okay. So this is as we change the input strength. Okay? Low input strength, you just get steady state. Both populations are just sort of firing at a very low rate. If you increase the stimulus strength enough, you see alternating oscillations. If you increase the strength more, one is up and one is down. Stationary. Okay? Increase more, you get to that Levelt branch of alternation. And increase farther, both populations are up at high activity, no more oscillations. Okay? So that's summarized in a diagram that looks like this. This is the input strength. This is the response diagram. Okay? Low input strength, steady response. High input strength, steady response. Modest input strength, alternating rivalry oscillations. Alternating rivalry oscillations. And in here, we have winner-take-all behavior. Locked. Okay? Like this. And you can do mathematical analysis of this. The model is simple enough that you can do analytic treatment of some of these features. Like this is a Hopf bifurcation to oscillate. Anybody know what a Hopf bifurcation is? How many? Let me see. Okay. All right. This is a pitchfork bifurcation right in here. Okay? Perfect symmetric steady state. All right. So you can do that stuff, and that's what this slide is about. And that's in this paper right here. I may have given it. It may be on the website. I don't know. I'm not going to go over this mathematical stuff, but it's there if you want to see some of it. Okay. What I like to do, though, is show you phase planes. I can't give a talk without showing some phase planes. Who's seen a phase plane before? Okay, good. All right, so the way I like to dissect these models is to realize that there's a fast time scale and a slow time scale. Okay? So the way I think about this is there's fast variables, R1 and R2, the firing rates. And then there's the slow variables, A1 and A2, the negative feedback. So for now, I'm going to freeze those slow variables. Treat them as parameters. And look at the dynamics. Look at the dynamics between R1 and R2. That's a phase plane problem. Okay? And there's two nullclines, the R1 nullcline and the R2 nullcline. This is a case of mutual inhibition. Okay? So you basically just draw their input-output functions. Okay? And these nullclines intersect at 3 places. This is population 2 dominant. Population 1 is not firing. This is population 1 dominant. Okay? And in between is some saddle point. So if I start down here, population 1 wins. If I start here, population 2 wins. So this is what you expect. This is winner take all on the fast time scale. So how do you get the alternations? Well, these nullclines change slowly with time because A1 and A2 are doing their thing. Okay? So this state down here, as these nullclines drift around, this state intersects with that saddle point and disappears. So there's only one attractor left, and the system switches to that state. Okay? So we'll look at a movie now. First, so this structure of 2 attractors with a saddle point in between forms the basis of many decision-making models. Okay, if you look at the work of Xiaojing Wang, two alternative force choice tasks. You have to say yes or you have to say no. You have 2 attractors. You start down here somewhere and noise is moving you along, and you finally go to one place or the other as you accumulate evidence. Okay? In this case, we let the process go on. We don't terminate the trial when you cross some decision threshold. Okay? This is ongoing, and you can get these alternations with the slow negative feedback. Okay, so here is those 2 nullclines, and now I'm going to turn time on, and you'll see those nullclines drift through each other. Okay, so now population 1 is dominant, saddle node bifurcation, population 2, population 1, population 2, and you'll see A1 and A2 are going on a negative diagonal. One is recovering from adaptation, the other is growing adaptation. Okay, do it one more time. And I want you to look at where the switch is taking place. Okay? The switch is taking place with the blue one saturated, the red one saturated, but the other one is halfway along its activation curve. Okay? The one that is suppressed is halfway along its activation curve. So the normal way you would intuit a switch is that the dominant one would fatigue and release the opposite population. Okay? But that's not what's happening here. Okay? The dominant one is not falling down on its activation curve, it's saturated. What's rather happening is the suppressed one is moving up its activation curve. It is escaping from being inhibited. Okay? So this is a mechanism called escape rather than release. Okay? You can see these kind of behaviors in central pattern generators. It's been shown experimentally, and it happens in these kind of models. 2 mechanisms, release or escape. Okay? This is the escape mechanism, and it corresponds to the Levelt branch. Okay? These parameters for this simulation were on this branch. Okay? If I would fix the parameters, the intensity over here, you would see the release mechanism, but there's no need to go through that. Okay, so the switch happens because there's a coalescence of a saddle and an attractor, disappear, and you make